Session. My name is Pete Barber. I'm on the program committee, I work for VeriSign. I'm looking forward to these next three presentations. These are all focused on measurement. The first of our three presentations is from Alejandro Costa, and he will be giving a presentation on identifying open resolvers in IPv6.
Hello. Well, good morning. Thank you so much for the presentation. My name is Alejandro Acosta. I work for LACNIC in the research and development team. I am the coordinator. First, I want to say and to thanks to Darío Gomez. He's a colleague of me. He works in LACNIC too, and he worked a lot in this project. Well, as the title says, basically what I want to show you is a work for identifying open resolvers in IPv6. What is all this about? It is very simple. And all of you know that to identify DNS open resolvers in the IPv4 world is quite easy. Basically, any computer in a couple of hours or day can scan every IPv4 address and to check if there is a recursion or not on it, and then identify if it is an open resolver or not. To do this in IPv6 is quite different. We need to take a different approach. We cannot scan every IPv6 address. There is no time for it. Why we did it, I am not going to enter a lot into these details. I know that all of you know better than me about why it is bad to have open resolvers in our network. Basically, you know that it is going to consume part of your bandwidth, it is going to consume CPU, memory, and a lot more. And of course, there could be, when you have open resolvers, evil attacks, even malicious from hackers, crackers, bad people, that is going to use your server. However, we are pretty aware that there are open resolvers that are open intentionally. So the people left the server open, like Google did, like VeriSign did, and many other operators. Okay, basically, now I want to show you the approach that we took to do this. This is the second research that is about this topic. RIPE NCC did another one last year, but they did it in a different way. Basically, the first step that we did was just a TCP dump, well, of course, after we do the TCP dump, we are getting a pcap file, as it has been mentioned many times. I feel more or less bad now that I heard about pcap and other libraries that you have, the DNS Cap and other utilities. Basically, we are TCP dumping a server that is called D. This is not the root server D. It is the reverse DNS root server D that is administered by us, by LACNIC. Then the second step is obviously to process this pcap file. We are doing it basically with Python. We are using a library called PyChark. And basically, it allows us to read the pcap and extract information that was obtained on it. Well, we are also using bash and to eliminate duplicates, IPv6 addresses, and much more. With TCP dump, in the first step, we are getting about 5 million packets in this moment per day. Maybe it is not that much, maybe it is not less, but it is a good number for our research. Finally, one more time with Python, with the DNS library, we are checking against every IPv6 address that we obtained in the previous step. We are checking if there is an open resolver or not. So, in the second step, right up, we are getting just IPv6 addresses that are resolvers. And in this step, we are checking if that IPv6 address is an open resolver or not, we are also able to obtain certain messages like query refuse, maybe if it is a timeout, etc. And finally, the ongoing phase, and this is the first event and first time that we're going to show our results. We are processing, cleaning, and publishing the data, okay? The results that we were able to obtain, for example, are number of IPv6 resolvers identified, number of resolvers per RIR, if they are open or not. And the final line, during our study, we were able to identify one more finding that I cannot expect better place than this event to show, okay? Basically, these are partial results. They are raw data. In the following slides, there are some graphs. I'm going to try to be brief on this. We found about 5,000 DNS servers in IPv6. For me, it was like a shock to see that Matt Larson show a smaller number. He showed something like 3,000 something. We found more than 5,000. And you can see how many are non-resolvers. Some of them are open resolvers. Let's talk about the ARIN region. What is the ARIN region? We found 78 on your right, fourth line. 78 open resolvers in ARIN region. Almost 1,500 are not open resolvers. So it is nice to see this. These are IPv6 addresses that are potentially can be attacked and used by people. In LACNIC specifically, we found 4 open resolvers. Here is the information. I tried to obfuscate a little bit the data. You can see in the first line the IPv6 address. There are no errors. It means that it allows recursion. And on your right is the owner ID of the IPv6 address. Here is more or less the same results, but in columns. You can see that, for example, Afrinic was an interesting case because we found 17 resolvers in Afrinic region, but none of them are open. So it is nice. I mean, somehow we know that 17 is not a big number. But for example, for RIPE, we have people from all the regions here. We found 36 open resolvers, most right, and 3,454 that are not open resolvers. Here is the same data, now shown in a different way, pie charts, but in percentages. And this one is one that I really wanted to share. Well, I really wanted to share all of this, with the number of resolvers per /64. For us, I was in shock about this. I have to say that I manually check not most, but I check a lot of this data to see if the finding was really an open resolver. I sent queries to many of them to see if what I was getting was real values. So the number of resolvers per /64, we found, for example, 62 resolvers in only one /64. That is a huge number from my point of view. Actually, maybe you can enlighten me with why do you think that it is happening? This is something, from my point of view, very interesting. I do not have an answer for this. I can think in a couple of reasons for this. Well, you can see we found many different prefixes that have a lot of dozens of open resolvers. These are not open resolvers. They are just resolvers in one /64. Big number. And actually, I believe, well, now we are working on the automation of all this. This is an ongoing phase. We expect to have this ready maybe in less than a month. And part of our goal is to create alarms and to notify the owner of the network that there is an open resolver, something like sending an email with the IPv6 address, something like that. And that's all what I have to show. Thank you.
There's no more paper telling me where to stand. Can you go back, I think, 2 slides to the one that has, yeah.
State your name, please.
Oh, sorry, Warren Kamari. So I suspect that at least one case of this, or one instance of this, is simply v6 privacy addresses, right? If you have one machine that is sitting there with an open resolver and it has a bunch of privacy addresses, it's likely to be listening on all of them. And so that seems like possibly a reason for, I mean, maybe not all of them, but at least for some of those, I'm guessing privacy addresses would.
That could be a reason, perfectly, of course.
Rafael Akamai, another possibility could be just box behind load balancer. So what you are actually measuring, the data you are getting is the data of the resolver IP used for query your authoritative server. That
Exactly.
might not actually be the resolver IP that users or customers are using to query that IP address. And with regards to that, I have a question. Have you checked which addresses are actually answering on that address, or which are just dropping the packet? Is there a distinction between these two cases?
Yes, we are checking in the open resolver the answer and the return message of the server. Was that your question?
The normal behavior of a recursor, if it's not resolving but listening on that port, is it will give you back your refused answer. So I want to see the distinction between refused and simply not answering. Do you have that data?
Yes, I have the data. I didn't show it here. With Python 3, the DNS module allows you to see some returns value. Sometimes I can see, you capture the exception, is exactly what we are doing here. And we have about 3 different errors. Maybe I can show it with you in private if you want.
Thanks.
Hi, this is Anand Buddhadev from the RIPE NCC. I had a question for you. You pointed out in one of your slides that you would like to notify users who are running open resolvers. My question is related but not quite the same. As LACNIC, do you do any checks of name servers pre-delegation when accepting reverse DNS delegation requests? Because we do that at the RIPE NCC using DNS check and now Zone Master, and any name server that is an open recursor is rejected, and we do not accept reverse delegation until the user fixes this. So this helps keep the number of open resolvers in our region at least, down. And does LACNIC do the same, or do you intend to do the same?
Okay. When a member of LACNIC, he goes to our website and he tries to configure the authoritative name servers for the prefixes, our system checks if they actually are responding to the prefixes. However, I do not believe that we are checking if also it allows recursion. It is a terrific idea. I'm going to double check internally, and if we are not, I'm going to say it because I believe it is a terrific, something that we have to do. Thank you for that, for pointing that out. Okay.
All right, thank you very much. Our next speaker is Paul Hoffman from ICANN. He'll be speaking about using DIDL data to look at leaked queries. Paul?
Cool, thanks. So I just realized as I was looking at my slides a little bit earlier, this is DIDL 2017. So I actually talk about that in there. Some people are looking forward to DIDL 2018, just want to be clear. What I want to talk about today is, because many people are worried about, wondering, or not worried, but wondering, how many of these queries are leaked? What are we seeing at the root servers that are leaked? And in order to do that, you need to look at the data. DIDL is one of the things that we've used for many years. Those of you who are familiar with the new GTLD program from 5 years ago, we looked at a bunch of DIDL data, got some things. So that's in the past. We have DIDL 2017 data, and I'll show you how I analyze that. And then there's going to be another DIDL coming up. that will be different in some ways. I'll talk a little bit about that. But again, most of what I'm talking about here is how you can look at the DIDL data as DIDL data to find leaked queries. At the end, though, I sort of go off to the side because one of the other things we hear in talking about DIDL data is root servers see so many addresses per day. And I do a bit of analysis on that with what I hope is an interesting result. So in DIDL 2017, just the raw data set itself, which is a bunch of gzipped files, is about 5.3 terabytes. And that's about, just sort of by odd chance, 530,000 gzipped PCAP files. Organization is a little bit funky. Thanks to Dwayne, it gets better. There's a sort of a second set. But basically, if you go through all of those line by line, you have about 118 billion lines. Not necessarily, that's not all information you necessarily want to see. And as we know, different root operators have more or fewer queries, but also the way that they gang their PCAP files are different. So this is, I'm just saying this as a, if you're going to be doing this analysis later, don't get fooled, just by looking at certain letters and such like that. There's also sort of a wide variety of how the PCAP files are named, but once you start doing your own analysis, and you'll see this, you make up your own names, you get going. And one thing to note for DIDL 2017, and I didn't look at previous years, is there's no data from US DoD, the groot operator. And by the way, so some of you have noticed that, or will notice, I'm trying to go with the new regime that the root operators are asking for, is that you don't always do everything just by the letter, that you actually try to say who's the operator and do the letter. I may or may not succeed at that. But anyways, instead of saying just groot, I'm saying from DoD. So DIDL 2017 has data from every other root operator, but G is missing. I'm sorry, US DoD is missing. So there's a couple steps in order to do it because you have all these PCAP files. So you read them, and what I did was I wrote my own extension for DNS DNS Cap, right? I was going through all of them, right? DNS Cap that puts out as text the source address, the RD bit, the Q type, and the Q name. And I started off by just doing the Q type and Q name. It turns out I really only care about the Q name, but then I started being interested in the source address. I'm going to end up changing this before all the software is ready, but this is something you can do in DNS Cap, is you can write your own extensions. I did it, like I say, just as text with a space delimiter so that you can go through and either grep or just in Python do your favorite thing. So that comes out for all of DIDL 2017 is about 4.2 terabytes. And the reason I keep talking about sizes here is not to be impressive because everyone's used to larger data sets. But when I get to the middle of the presentation, I'll talk about how that affected how I could do the analysis. So I kept the output file names. I used the letter. I didn't spell out ICANN and US DoD or whatever, just so that if I wanted to do a later analysis by letter, I could do it. And then just to show, like, this was something from the file that came from H. Again, 4 fields, and this is literally space delimited. And this is the kind of stuff you see going to the root operator. And just to be clear, all of these PCAPs, or all the PCAPs for operators that have IPv4 and v6 on, the same instance, you'll see both of those, and you'll see host names that you would not call host names. And for example, there is the 5th one down has a /032 for, non-ASCII characters get spread out by this. Everything that you've heard before about, oh, there's a lot of crap going to the root server is completely true. And so this is what you see on doing this, and there's 4.2 terabytes of this. So once, again, what I wanted to do is to make a collection of the TLD scene so that we could say what is being leaked. But because, let me, or if you look here, further down, notice that all of these are likely to be unique TLDs that one is seeing. In fact, that's the whole host name. So somebody's sending a query for just a TLD that is the entire host name, and it's clearly a random string. Not completely random because there's no digits in it. Don't know why they chose that. But this totally makes doing this analysis difficult unless you have an infinite amount of RAM or an infinite amount of time where you can cycle through and be very careful. This is, as you'll see once I get to the actual data, and by the way, this was not cherry-picked. So on this slide, these were the first 5 or 6 lines from that file. Same file, maybe another 5 down. These were all in order. This was not like, oh, I found the bad ones. These all came right next to each other in time. And you'll notice they're all from different places. So the way I got around the memory issues was that I picked a subset, because in fact, if what we care about really are leakages, we care about the most common leakages, not every goddamn thing that the root server saw. So trying to make buckets, as anyone who's done this in the past, there's not a real science to making buckets so that you can stay in your right memory limit. So I churned a bunch and did that. Then I realized as I was doing this, and I really wasn't getting very far on would this work in memory. I would just, every time I would do a run, it would just like run out of memory and scream and die. I realized that you could actually take the names that are in the root zone. Those aren't leaked. So you can sort of push those off to the side. And there are some leaked names that we already know about. RFC 6761 registry, which doesn't have a large number, but those are ones that we see. Maybe put those off to the side. The inter-aisle report from 2012, which used the diddle data, if you take the top 100, some of those which are real names, but a lot of the inter-aisle report, which is what the corp home and mail stuff was based on, we know that those were being leaked then. They're probably sort of considered leaky now, except for the ones that have actually been delegated. Put those off to the side. And in fact, take the whole set of GTLD delegations, whether they've been put or not. These are things that we know about. This would make it a little bit easier. And then I did, and then the P2P specials internet draft, which never got into 6761, which had a couple of those, is like, okay, these are things that we'll know about. Then I split some of the results into the things that have a dot and things that don't have a dot. Because if we're thinking about leakages, something that is just a TLD that's going to the root server, that either is not really being leaked or it's being leaked by something that is using QName minimization. But we know that QName minimization isn't being used that much these days yet. So just as a general bucket, threw that off to the side. And then if you look at a sample of just 10% of those 500,000 files, then you can actually stay within your memory. So the reason why I'm having all these caveats here is when you start seeing my data, do not take it as definitive. I had to keep sort of grinding through to get something. It's believable, but it's like everything in the DNS, we see lots and lots of anomalous stuff. And you'll see later as I start talking about the fact we're going to look at this for LRoot as well, you'll see different things based on where you're looking and which days you're looking. So for diddle, and I'm sorry again, I didn't say diddle 2017, looking at all of the results. The first thing, let me just explain what the columns are. The rank is clearly biggest to smallest. The string, the two, number 1 and number 3, I'll explain in a second. The number of counts in hundreds of thousands. And then what you see as an I there is something that was in the inter-aisle report from 2012. That's why I'm saying I use these as a way of identifying things. Something with a 6 is in the RFC 6761, and A is something that there is currently an application for. Currently at the time, obviously that has now changed in the last few weeks, but so TLD _no _sub is a plain TLD that didn't have a dot in it. TLD with sub is something that had a dot in it. Warren, are you going to interrupt me or are you? Okay, fine. So what we see here is COM. Everyone expected COM to be up there. But look how much smaller COM is than just clearly some random string that you didn't see very often, that you didn't even see in the top 10,000, is so much bigger than COM. That sort of gives you an estimate of how bad is what we're seeing. And net, and then, dot, fortunately people are asking the root about the root, and on down. And I won't go into all of these. Now, just of the results that are not in the root, so things that really aren't there, again, those top 2, the same things, And now we have a bunch of things that you almost might recognize. You see some router vendor names, you know, D-Link and Belkin. You see localhost, okay. You do see corp and home in there. You don't see mail. But looking at this, if you're considering looking at leakages for, oh, well, I'm on SSAC, we're supposed to be looking at corp, home, and mail and such, notice that there's a lot between corp and home that we have not really talked about. And in fact, look at DHCP. DHCP was not even in the inter-aisle report 5 years ago, and yet it's now sort of, in some ways, more important than corp, and things like that. So again, these are the results of the top 17. I went down to, I think, 100 or 1,000, I forget. So are these actually leaked? We can't really know because we don't, you know, like we can start looking for heuristics, but we can't really say what is leaked and what is just being sent, you know, due to the tragedy of the commons. Z, DHCP, workgroup, and IP are new relative to what we saw 5 years ago. So this does indicate that, in fact, we are seeing new kinds of consistent, you know, things that might be leaked or garbage at the root. And now, the last bullet, I'm just going to skip over because it has nothing to do with technical. How can this inform the future? Don't know. You know, people are going to look at this in many different ways. We have ways to look at it. So what I want to go into quickly, because I am going to run out of time, when I said, gee, ran out of memory, I actually ran out of disk space when I started doing this, because as Keith had said yesterday, everyone is not deleting their files off of AN1. So I couldn't even keep the 4.2 terabytes of interim data. So folks at OARC gave me a new box, or they spun up a new box. They, you know, provisioned it. It's not mine. It's yours as well. So it's got 64 gigabytes of RAM, 15 terabyte hard disk. It's connected to the same network, so I can pull the stuff off as it's going. And it was extremely useful for me to be able to keep my interim data and not have to do it over the slow network. This is, and as Keith said, they're coming up with ways of maybe sharing this with you folks. Again, it's not my box at all. I've been using it. Someone else who wants to run my software or their own software will probably take it. Think of it maybe, and this is just a proposal, but it was what Dwayne had mentioned. Think of it as a library book. Maybe you get it for a month, and I should be done with it by then, or I could be warned that, you know, I'm going to have to turn it in to do analysis on the data. Okay, so now quickly I want to do this with not just with the diddle data, but ICANN's root, which is also known as L. We've got our own machines. Roy has been telling you about our machines and kind of thing we can do. It's similar. The results are similar. I'm just going to go straight into the results, but they're not exactly the same. So these look similar to the all results from a bit before, and then these look similar to the ones we had here. But some of the TLD queries for LRoot happen much more often than they did across the diddle data. I'm sorry, I should be clear. These numbers are actually from our own, on the same day of diddle. So what this says is, in fact, if you look at diddle, you will get a wider view than looking at onesie twosie. However, looking at onesie twosie is a lot easier. I didn't have to get a new machine. We had all this, you know, I could do this easier. In specific, even some of the non-leaked ones, like CCTLDs, had a different order in just looking at LRoot. And many people know, well, LRoot's very well distributed, but that very well distributed actually gives a different view of the root servers. So taking that, I mean, everyone knows who Korea and China are, you know, KR and CN. That will tell you why we are also seeing different orders of leaked data, right? Because even the non-leaked data, we can see very obviously, okay, this is very clear. So overall, the data was similar, but what this says is you can't say, this means this, because it really depends on who you're looking at. Now, as a diversion, since I was able to collect this, and this is my last bit, you know, we hear some things about, 4 million addresses seen and such like that. This was not why I had started doing this, but since I had the data, I had the boxes, I was doing this. So I thought, well, let's actually do some real counts on numbers of addresses seen, and which, by the way, will not be complete at all, because even for DIDL 2017, iRoot is anonymizing their data, and they're all in the 10 address space. So they're all in the 10 address space. So you know that they're not, that's not the thing. In DIDL 2018, we're expecting more people to be anonymizing. So any analysis of how many individual addresses are we seeing pretty much have to be from the past. There was also a question that where I added a little bit of data that you'll see, which is, well, maybe we can tell who's really not a recursor because they're not actually using the RD bit. It turned out that wasn't useful, but it was data that we had. So the following slides are just from LRoot, not from the entire DIDL. So if we looked at LRoot on DIDL day, we saw these numbers, N meaning that there was no QR bit, and R being that the QR bit was set. So total, RD bit, I'm sorry, RD bit, thank you, Roy. So that gives us some numbers. Now, what we did though was we looked at the whole week, starting the day before DIDL day and then going up. So if you go over a few columns, you'll see on the first day, the INCR column is incremental increase. So, from 0, everything's an incremental increase. If you look at, so we started the day before DIDL, and then looking at DIDL day, there's almost for all, a 25% increase in the number of unique IP addresses seen. So when somebody says we see this many unique IP addresses, that means on one day, if you looked at 2 days, your number would be 25% higher. And even if you look at 3 days, well, then it's going to be another 16%. So looking at the whole week, what we see is that going over the whole week, that you actually, the total increase is almost twice as many as if you'd looked at one day. You think, oh, okay, well, so we can start using that number. We should start saying number of IP addresses per week seen. But, and this is the thing that really messed with my head, a lot of those you saw less than once a day. Is that a real customer or not? Right? Who is running a recursor that would talk to the root, but talk to it less than once a day? And that's like half of the data. So I don't have any answers. I'm not going to give any answers here. But when we start saying numbers like this many addresses and such like that, we should be a lot more careful. So let me finish up. The software was supposed to be on GitHub before now, but I'm going to be refactoring it, and I'm going to be making sure it's going to work for DIDL day. So I will have it ready before DIDL 2018, I promise, and I'll post it and let everyone know. And so the other thing is, though, as you saw, we have all this LRoot data. ISI has a lot of BRoot data. People who own data. And so it may actually be better to do some of the analysis on individual roots where you have longer time frames than doing DIDL. DIDL is great for collecting it all together, but now we have lots of opportunities to use other people's data. So with that, great. I did it well. Thanks.
Warren Kamari, Google. Can you go back to, I think it's like slide 7, where you've got
Maybe.
yeah, probably that one.
Yep.
So up at the top, you've got a thing with TLD and no sub, and that's a whole bunch of random queries.
That's queries that did not have a period in them.
Yes. So I suspect that one of the big causes of that is when Chrome starts up, it sends
Could be.
3 queries between 7 and 15
Yep.
digits or characters.
Absolutely.
And it seems like it would fit perfectly into the examples that
Yep.
you showed.
Could be.
Okay.
So you're Warren Kamari from Google, right? Why isn't Google sending that to a server that they run instead of the roots?
So specifically what it does is it doesn't query the root, it queries the local recursive servers. And the reason it does that is it looks for things that do NX domain redirection and rewriting. So there's this reason that it has to query those specific servers. If it sent it to ours, we'd always be like, here's the real answer.
Yep, okay. And the reason I was poking at you, Warren, was this is a tragedy to the commons thing. I mean, this makes this data look much worse. Sorry.
Hi, Paulo Artus.
Yeah.
So first, the .z entry. I looked in some of these entries, and there is some alternative. ICANN has a monopoly on DNS names.
Sure.
And we're fixing it, and they're offering .z, so that's one of them.
Yep.
So I'm kind of curious if you also see .earth, .leopard, .cheetah, because those are
not in the top ones, but you know.
those are the same alternative register person.
Yep.
And then second,
So here's an interesting question. Is that a leak or not?
yes, it's a,
Right.
it's a leak
Right.
from
It's
an
not a-
alternative domain name system into the
Right.
real one.
It's a leak from a system running on the internet, but that is not supposed to come out. Yeah, exactly.
And then the second, you mentioned the resolver IPs that you see that only query you once or less than once a week.
Right.
Wouldn't that be perfectly normal, happy, up-to-date resolvers with query minimization?
No, because with query minimization, no. Right. So that would only be if somebody was asking them all their queries were for an extremely small number of TLDs.
Okay, let me rephrase it. Query minimization and running local root zone.
Well, if you're running local root zone, you shouldn't be talking to the root servers at all. So maybe if you're slaving,
I'll wait
yes,
for
you
the
get.
next coffee break, thank you.
Right, exactly. And so that might be it. That absolutely could be it. I'd be surprised if the numbers were that high, though. I'd be thrilled, but I'd be surprised.
Hi, Dwayne Wessels from VeriSign. Can you go back to that other slide 7 again? So you said TLD no sub is a name with no dot.
No dot, yep,
TLD with sub is a name with a dot.
right. Which, by the way, could be what looks to you and I like an IP address.
Okay. But then you've got on this list like DHCP and internal. I assume those had dots.
No, these.
Those are bare names. With
Yes,
no
these
dots?
the top two were uncategorized TLDs with no dots or dots. So, for example, looking in here, we actually saw a dot local that has a dot, Epson whatever dot local, and so those would be, those would appear as local.
Okay,
So I could separate them out.
So
I could separate these out by had a dot or didn't have a dot. I didn't do that.
Well, I guess what I'm trying to get is you have some categorization, apparently.
Yeah.
And how does that work?
It,
So why is internal or DHCP not in the TLD with
because
sub?
we saw them often enough. The
Okay.
top two are the ones that we saw like less than 1,000
So
times.
there's a cutoff at some
Yes,
point.
exactly
Okay.
right.
Okay.
Or else I would have run out of memory, even with doing that sub bit.
All right.
Yeah.
And-
So those were just heuristics that I was using so that I could finish running
Yeah.
in 64 gigabytes.
Yeah, okay.
Yeah.
So on slide 3, for anyone that doesn't know, what DNS OARC generally does with the diddle data is it's sort of in a raw, there's a set of raw files and a set of what we call clean files.
Right. Raw being, go ahead.
This
sorry.
sounds like you use the raw file, no? Well, you complained about file naming, and the clean file set has very consistent file naming, so I'm curious what you meant by that.
More consistent, not completely consistent. You and I can talk about that.
Okay.
At least I had to find them by using glob, not by like looking for example, some of the letters have multiple levels of subdirectories and some of them don't.
That doesn't sound right. So we need to talk.
Yeah, we will.
But-
And
but-
we should talk before April.
But to be clear for the audience, you used the clean data set.
Absolutely.
And did your analysis on that. Okay.
Correct.
Yeah.
Yeah, I actually found the raw data set. I just couldn't even make heads or tails of. So thank you for the clean.
So, Robellis ISC. Your RDBit stuff. So Roy and I, in a past life, did a lot of work on CutWhale. And I suspect that what you're seeing is that if you're seeing client queries come in with RDBit set for a bare legal TLD, so for example, just UK without, it looks as if it's been QNAM minimized.
Right.
And if the query ID is 0 in the top 8 bits, so it only uses 0 to 255, it is probably a CutWhale infested host.
Oh, okay.
Okay. Furthermore,
Roy, are you
CutWhale-
taking notes on this so that I know to look
Roy
for that?
remembers all this.
Yes, right. Yes.
It's just he hadn't seen your presentation before, so. Also, CutWhale's been around about 10 years, I think, now, but it has outdated root hints. And I can't remember
Great.
exactly which of the root letters it has the wrong IP addresses for, but there's a chance, if you're looking across the whole diddle data, that you will only see, I think by memory now, probably 9 of the 13 different root letters.
Okay.
And it's also IPv4 only. So it's
Okay.
IPv6. So
Great.
we'll
So
offline and get some
thank
more
you.
details.
I didn't know that, and we will, because Roy knows that and he's nodding his head. We will run that on current data. Remember, this was from diddle of last year. Of course, for LRoot, we have all the current stuff as well.
From memory, they excluded the DoD because I guess they didn't want to send stuff to the DoD root servers, and whichever the root servers have changed their root hints since roughly 10 years ago. So,
okay. Yeah. Great, thank you. Yeah.
Petr Paček, CZNIC. Do I remember correctly that the IP addresses of FreeSolvers which queried only once a week or something are just from the LRoot, right?
Yes.
Okay. Then one of the possible explanations is that different resolvers have different algorithms how to select the server, right? And if we find out that, for example, B is the fastest one, we may retry and go randomly to some other server once a day, once in 2 days, depends. So that might be one possible explanation.
Absolutely. And in fact, I think what is likely, although that still seems too low for this, because what we have for a lot of the resolvers is they have a minimum that anything, they don't look for just the fastest, they look for anything in a certain range, and lots of them are within that range. So I would have expected to see 6, it rotating around 6 times. That's definitely something I want to look at later. I would very much like to see how many of these really are that. Just 1 a day seems too low for me. Yeah.
Sure.
And by the way, this was a long tail. I mean, there were plenty that we saw 2 a day from or whatever, so.
Toma Gavrichenkov, Curator Labs. A short question. So nowhere on the slides are domains.onion and .i2p. So
right.
Yeah.
Good
so
point.
For you have an estimate that they are not queried. Oh, sorry.
Yep.
They are not present in the data, or almost.
They are. They're further down on the list. They're much further down on the list.
Oh, yeah.
Yeah.
Okay. Thanks.
Yeah. And like I said, but to me, what's interesting about that is those are ones that we've all heard about, those of us who fought the 67, 61 wars and such like that. And yet, here's a bunch of stuff that we didn't even know about.
Belkin.
Belkin we had heard of. OpenStack local. That's very, very new. And I did, by the way, get somebody who knew about why that's there and such like that. That's something that's very, very new that appears fairly high in this. And so going back to the question I didn't really want to deal with too much is, how is this going to inform people when they're trying to decide which things are too dangerous? We focused so much on corp, home, and mail, plus, then these 67, 61s, onion, and such like that. Looking at this, that's not the way, I'm not saying I know how we should focus, but things like onion, P2P and things like that, I would have thought that they would have been much higher than Davo link. Yeah, right, so. Okay, great, thanks.
I believe that's it. Thank you very much,
thank
Paul.
you.
All right, our next presentation is from Joe Adamas. Jeff Houston is also a co-author of this. This is field measurement of Anycast DNS route traffic delivery. Thank you.
Thank you. How do I switch the presentation?
Somebody has to click the things.
The main difference comes from the fact that we focus on human experience, and so therefore we exclude what might happen to automated processes and machines. The study we are presenting now was all done with queries targeted at KRoot exclusively, for which we thank the RipeNCC immensely, particularly because this was already done last year, and we have been presenting the outcome of what we found for long enough. So thank you for providing the data, and thank you for the patience bearing with us. So just a quick reminder, this is what a typical experimental setup looks when we try to do measurements on user experiments. So we use the Google Ad Platform to deliver ads to user devices, okay? So that itself has some caveats already. Google only presents ads to things that it believes have humans behind it, because ads are only of value to humans. Machines don't usually click on ads. So that's a subset of machines that could be out there. If you have a Windows Active Directory server, Google is going to try very hard not to present an ad to that thing. A large proportion of these is mobile devices, because that actually reflects the usage pattern of the internet these days. And it's not only presented to web browsers, by the way. A lot of applications, particularly mobile applications, and the ones, games typically, that you see are free to download and then play, make their money by showing you ads, by embedding operating system kits, like Apple's WebKit, to behave like a browser and present an ad to a user that's watching the screen. So this not strictly just people going around in Chrome or Safari or whatever, right? When the ad is delivered to the user, the first thing the ad does is come to us and ask us for a few lines of configuration. We deliver this configuration. So, and that's actually where the test is, not so much in the ad itself, but on what we ask the user to do, to perform, to be able to get to a resource later on. So on this goes through several steps. And so on the first thing, when the user comes to us and asks for the configuration, we get a direct interaction between the end user device and ourselves. So we know things like the end user IP address. Of course, we know what configuration of an ad we deliver to the user, which we'll say later on. When the user then tries to access the URL, it asks typically its resolver to do some work for it to resolve the name, right? In that step, because the DNS queries are going to come to our servers, we learn about what resolvers that particular user is using at any given time, and it's usually more than one. When that query shows up at the root, and this we do basically by rewriting the query when it comes to our name server and delegating that new name to the root, even if it's not really there. We just want to force the resolver to send the query to the root server. It's kind of a false delegation. And because it's within the rules of DNS, resolvers follow it. So we then look at the root server data, and from that we learn what the resolver was trying to do. And also we get to learn a little bit about what's in the search list of the initial client. So the local configuration may add local domains, and that's what we are showing. For us, this was kind of a byproduct, but I'll show you the results later because they are different from pure passive observation of everything that shows at the root server. So what do we see after all these things? Amazingly, Anycast routing is better than I ever expected from having heard previous presentations, at least for KRoot. Their mapping of which resolvers get to use the closest Anycast node is amazingly good. So much so that that's the entire list of resolvers that were in one country and asked a node in another country. That's the entire list out of 3 million separate instances of tests we conducted. Okay? It doesn't get much better than that, I think. Especially because some of those are actually close by. So like if I see a server in Kenya, a resolver in Kenya, reaching out to a root server in Johannesburg, okay, that's not too far-fetched. Okay? So I was surprised at how good the mapping actually has been. I was curious about looking at the LRoot data because they have a different NCAS deployment methodology. The problem is LRoot data is in CBOR format, and then that proved too time-consuming. So if OARC were to produce a tool to currently make it easy to parse CBOR, that would be really handy. Okay, so I was astonished by that. The end-user experience, however, doesn't depend only on how good the resolver is at reaching the authority server. It also depends on how good the user is at reaching its resolver. And that's not as good as in the case of resolver to anycast node. There's a lot more people who make choices, deliberate choices that make their own systems ask resolvers that are not close by. Looking at the data, I was again surprised because the usual response is like, well, surely people are just using Google DNS and this is not close by, so they end up in far-fetched places to go there to get their DNS data. Turns out that's not the case. But apparently, Google has a pretty decent worldwide deployment of resolvers for 8.8.8 that gets the answer there. Most of these, over 76%, probably more around 80%, but I stopped counting after getting bored, is actually people using OpenDNS. That's a very deliberate choice. I'm not showing you the data about the countries, but just to give you a hint, the typical users that choose to use OpenDNS over others are located in countries like Egypt, Palestine, Bahrain, and people basically seem to be using OpenDNS because of their last mile encryption, which actually provides anonymity. Whereas if you use Google, you'd still be exposed to what you're asking. So that's an interesting thought. The second most used provider, by the way, was Yandex, which is a Russian provider. So some people have different reasons, apparently. Okay, so one of the byproducts which I mentioned, and this is to compare with Paul's presentation, user devices and how they behave. You see some of the TLDs showing up because they get tucked to the end of the query. So the RIPE-NCC, when collecting the data, was not giving us a full feed of data. It was providing us only with the queries they saw that contained our string. We told them what we would be producing, so they filtered on that. That makes life easier for everyone when sharing data, because we only look at things that we already knew we were producing, and so less trouble for everyone. So these are the ones that were human devices that we targeted. From the 3 million of them, a very small number leaked queries that had these non-existent TLDs added to the end. And of all of those, the vast majority were home. Okay? Then some of them you see in Paul's presentation, some of them you do not see. For instance, workgroup is absent because that's usually Windows-to-Windows communication taking place in the local network that managed to escape. That is never going to be generated by your browser or your iPhone or your Android device. So basically that's it. One thing this provides, by the way, is a filter, a way for you to separate which of the total data set that you see at the root servers is generated by human devices versus automated devices. So MAP may be another parameter that people, when looking at policy and what might break and not break, can take into consideration. How important is it to break a human being using a device, accessing the data, versus some other machine that should not actually be sending the query anyway? And that's the end of it for us. We'll probably do this again sometime in the future. Any questions?
Hi, this is Andrew Sullivan. Could you, oh, and I don't speak for anyone, could you go back a couple of slides? This one. The thing that, maybe I just missed the step on the previous thing where you were explaining about, but how are you sure that these are closer?
That these are closer because the routing system says so. That's where the packets ended up. So these are packets exited a resolver with a given source IP address and ended up at a node. Okay? So for them, for their network view, it was closer.
Obviously, I mean, these are the ones that they landed. I guess what I'm wondering is, it seems to me that, I mean, because of the way you're testing this, if your test mechanism and the routing system has the same geo-topological bias built in, so that they both think that the network topology and the geography map this way, then this is going to be the obvious conclusion. Like, it'll be necessarily true because
none of these. Bias. So you have to fear that none of these two endpoints that you're seeing listed there is under our control. One of them is the root servers.
Yeah.
The other one is the ISPs, resolvers, or whoever resolvers people are using. Okay? We target the end user, and then the end user uses its own configuration to go fetch stuff, right?
Right.
So if you are, what I'm saying is basically ISPs have their routing pretty well figured out.
Well, okay, I think I'm not making my question clear.
Maybe.
So I'll try to reformulate it. We can talk at lunch or something. Thanks.
Sure.
Brian Harvickson, OpenDNS. Just a quick comment. You mentioned you saw the number 2 is Yandex onto that privacy stuff that you were talking about. They also run DNS capable.
Oh, they do.
resolvers.
Excellent.
So
see?
that
Learn something
may
every day.
have
So
something
it's
to do with it.
cool. So people really care about this. That's where you see most of the mismatches. They will take that step very consciously. Okay, thank you.
Okay, that's all the questions. Thank you very much for the presentation. And I know everybody is really excited about lunch, but I have some announcements before I let you go. So first announcement is I would like to point out Mr. Jerry in the back of the room there. He is giving demonstrations of the DNS JIT. Would you wave your hand to the audience? Thank you. So if you would go back there and give him an opportunity to show you his DNS JIT, he would love to tell you about that. Next item is that Dinesh tells me that he's not going to let anyone have lunch until they fill a survey, but Keith tells me the survey is not ready yet, so we're good for the lunch. So they're still working out some technical issues with the survey, so we still really want you to fill in the survey. As a member of the program committee, that is a very important part of the feedback process so that we give you guys a selection of good presentations for this OARC. The Net Girls session will also be happening, so please, if you're interested, please go see Sue. And the last item is we have the PGP signing party is at 13:15. Matt, would you raise your hand? Matt Poundsett, there you are. So this is the guy who's going to be coordinating all of the fingerprints and such. If you would like to have your PGP key signed by lots of people in this room, this is the place to do it. 13:15 will be happening right here. Oh, so even though the schedule says at 13:15, it's a lie. I want you to count right now. Oh, you want to come talk? Yeah. All right. I believe that is all the announcements. Now you may rush to lunch, which is served right outside. We'll be reconvening on our normal scheduled time, and that will be at 1400 local. Thank you.